In this video, we are going to take a look at how we arrive at this result. Differential coefficient of x to the power n is nx to the power of n minus 1. Let's see how this graph looks like when we plot it on the xy curve. So as x increases, consider this function fx equal to x to the power n, and this is the function we are trying to plot. As x increases, fx increases, and depending upon the value of x, this function will grow faster if n is higher. So the function, if n is higher, the curve could look like this. If n is smaller, the curve could look more like this. If n is, for example, even, the function will be symmetrical like this. For example, if n is 2, is fx equal to x square is a regular parabola. But if n is negative, like n is equal to 3, then this function will go like this, because for negative value of x, the function will have negative values. Consider a particular value at x equal to x, and we are trying to find out the value of the gradient, the differentials at this particular point of the line touching at that particular point. To find the gradient of the line touching this particular curve at this point, one trick is find a point very close to it, like here, and try to find a point very near to it and join these two lines. And this line is at x, the point very near to this one is x plus h. The value of this function at x is fx, and the value of the function at x equal to x plus h at this point will be given by f x plus h. The gradient of this line will be given by the rise divided by the run. So I am interested in finding out the function, the rise, which is fx plus h, minus fx, that is the rise, divided by the run, and this run is h. And I want my result to be as accurate as possible, and to be able to as accurate as possible, I will have to make this h as small as possible to get a more accurate result. So just to make sure it looks like this. So if I write it as limit h tending to 0, and this is the definition of the differentiation of a function fx. X to the power n is our fx. Now I substitute these values, so I get limit h tending to 0, x at x plus h, this value will be x plus h to the power of n, and minus fx is x to the power n. This whole thing is divided by h, and this equals I can take x common from here, so I get x to the power n. Inside the bracket we have 1 plus h upon x to the power of n minus x to the power n divided by h, and this I can write it as limit as h tending to 0. I can expand this as a binomial theorem, 1 plus nx, so 1 plus n into h upon x plus n into n minus 1 divided by factorial 2 h by x whole square plus and so on and so forth minus x to the power n divided by h. At this point, we can see that we can simplify this one a little bit. How we simplified it? When we will expand this in the next step, is x to the power 1 into 1 cancels out with minus x to the power. Now this x and this x to the power n becomes x to the power n h x to the power of n minus 1. This is our primary concern term, as we will see next step. This becomes n into n minus 1 divided by factorial 2 multiplied by h square x to the power of n minus 2, and the rest of the terms I will see is not needed. The whole thing divided by h. Now from here h gets cancelled out. From here this h will cancel out, will become h to the power of 1, and in the next one h to the power 2, etc., etc. At this point of time, you can see that as limit x h tends to 0, all these terms will go 0 because we have an h term here in each one of them, and others have some significant value. So what the result means that this becomes n x to the power of n minus 1, and that is the proof of n x to the power n minus 1 that you will memorize and use it in solving all your differential calculus problems.